How's it going, class? So this is going to be our next lecture, our eighth lecture. We're going to continue on our trend looking at training principles. On this one, we're going to be looking specifically at aerobic training. So we'll jump into it now, share my screen with you. We'll jump on in. Yeah. All right, so adaptations for aerobic endurance. So we'll start with a brief review. Remember our Krebs cycle. We remember our electron transport chain. We remember glycolysis, right? So this is how we produce ATP for long duration, low intensity bouts. Right? We start with glycolysis, where we break down our pyruvate. We break down our glucose into pyruvate, ship that into the Krebs cycle. So we ship this pyruvate into the Krebs cycle, and then we move ship the pyruvate into the Krebs cycle, and then we move our high energy electron carriers, or NADHs, move them down to the electron transport chain, where they create this hydrogen gradient and use the ATP synthase to mechanically create ATP. And so we get one glucose molecule will give us 32 or 33 ATP molecules. Remember, the glycogen gives 33, glucose will give us 32, and then one free fatty acid, which comes in right here with an acetyl-CoA. Free fatty acid enters the Krebs cycle in the same area as the pyruvate does. That gives us 100 plus ATPs. So fat yields 3 to 4 times as much ATP compared to carbohydrates. But again, it's a more efficient process, which means it's a slower process, so it's not good for higher intensity exercise. Well, this should be a review of our blood to muscle. Oxygenated blood is transported via the arteries, specifically away from the heart. Oxygen diffuses across the capillaries into the muscle. As the muscle requires more oxygen, that means that there will be more oxygen diffusing across the capillaries into the muscle. That is what drives the gradient for muscle oxygenation. CO2 is removed from the muscle via the capillary and transferred back to the heart and to the lungs, so it can be exhaled out. And then oxygen delivery improves with training. So cardiac output, AVO2 difference, and blood volume, which we'll all talk about in this lecture. So aerobic capacity, the ability of the muscles to use oxygen received from the heart and lungs to produce ATP. My face is in the way there, I'll move that. To produce energy, the rate at which the body can use oxygen, and ATP production from aerobic pathways. So VO2 max is the maximal rate of oxygen consumption, the maximal rate at which your body can utilize oxygen to produce ATP. And a lot of this is going to be reviewed. You might have heard this before, but it's setting the foundation of what we're going to talk about later in this lecture. So O2 means oxygen, max means maximum, pretty simple. And then the Fick equation, that is our VO2 max. So VO2 equals blood flow, cardiac output, times AVO2 difference. And if you remember what AVO2 difference is, that is the difference in oxygen from the arterial side to the venous side. And if there's a greater change in oxygen from the arterial side to the venous side, that means more oxygen is being extracted by the muscles. So if you have increased blood flow and increased oxygen extraction by the muscles, that means that you must be consuming more oxygen, hence a higher VO2 max. And then we remember that we have absolute, which is just liters per minute. So that is just the amount of oxygen that you're consuming in total, versus relative, which is relative to your body mass. That is how much oxygen you're consuming per kilogram of body mass, which is a little bit more important when actually talking about VO2 for aerobic fitness, because it is individualized to the person. So endurance, muscular or cardiorespiratory. So these things kind of get overlapped a little bit. Muscular endurance, as it becomes more long duration, becomes more cardiorespiratory fitness. So there's a few different factors. You have psychological factors, your motivation and your pain tolerance. You have physiological factors, your brain glucose, VO2 max, body temperature, muscle glycogen, fat oxidation, and then you have biomechanical factors, your flexibility, your elasticity of your tissues, your healthy bones, how heavy you are, what the length of those bones are. Quite a few different things play in. So your heart rate response to exercise. Heart rate increases linearly as exercise intensity increases. So this is mostly true. So we see here, as exercise intensity increases, as we're using more and more of our VO2 max, we see heart rate is increasing mostly linearly. And this is not a direct relationship, but it is mostly true for most populations. So your heart rate will also plateau in steady state exercise. So as you get to a certain exercise intensity, your heart rate will plateau. And so you will see here at the same intensity, a more fit person's heart rate will plateau at a lower increment. And that makes sense. The more fit you are, the less hard or the less beats your heart needs to make at any given intensity because your stroke volume is higher. Blood flow during exercise. We should know this. We should remember that blood flow is redistributed throughout the body during exercise. So it's taken away, it's shunted away from the internal organs that don't need it as much. You're not sending as much to the liver or to the kidneys or to the stomach, the GI tract, because most of it is being shunted and sent to the skeletal muscles. We look down this chart here, we see skeletal muscle at rest, and then compared to it at exercise, we see there is a massive increase massive increase in the blood flow to the muscles. And that's because the muscles are the metabolic tissue that are most requiring that oxygen supply at that time. A volume of blood moving also increases. The amount of blood that you are pumping through, the rate which you're pumping it through is also increasing, as well as if you are more aerobically fit, you are going to have higher blood volumes in general. So again, talking about cardiac drift, so increased demand for blood. So as you go through cardiac drift, essentially as you go through long-term exercise, and as you begin to become dehydrated and begin to become severely fatigued, you begin to see your stroke volume go down. And because your stroke volume is going down, your heart rate needs to go up to attempt to maintain cardiac output. But because your stroke volume is going down so much, becoming so dehydrated, your cardiac output is also drifting down. Your blood volume is drifting down because you are dehydrated. Skin blood flow is going down because you're dehydrated, which means that you are becoming or you're having an increased body temperature, which is also leading to fatigue. Cardiac drift is essentially the phenomenon which you are exercising in which your cardiac system becomes more inefficient over time. And so looking at this, physiological responses to acute endurance exercise. So we can look at these different things here. I'm not going to go over them in too great detail, but you can see here the blood flow distribution, the blood flow change. You can see how cardiac output and the hemoconcentration changes. You can look at arterial dilation. You can look at this whole graph here and see what's occurring. I'm not going to go over this in any greater detail because you guys can look at this and understand this yourselves. So adaptations to aerobic training. This is another graph kind of looking at that. We're seeing what's happening. So we see here that VO2 is dependent on flow, right? Stroke volume and heart rate, and then AVO2 difference. So you're going to be modulating how much blood flow you can get to the muscles, as well as modulating how capable those muscles are of drawing in oxygen. And so let's say you increase the amount of mitochondria in the muscle. That means the muscles have a greater capacity to utilize oxygen, which means that this AVO2 difference is likely going to increase because the muscles are more efficient at utilizing that oxygen. And so successful endurance athletes have a few different predominant characteristics. So the most important one, or most common, is going to be the VO2 max. You need a high VO2 max to be able to perform at high capacities in aerobic sports. Next is your lactate threshold, percentage of VO2 max. So you want your lactate threshold to be high. Think of lactate threshold at the maximal capacity that you can work before you begin to fatigue rapidly. And then your economy of effort. You want to make sure that at any given work rate, you are working at your most economical. If you have athlete B versus athlete A, and athlete B is using less energy than athlete A to do the same amount of work, they can be said that athlete B is more economical. And then as well as you're going to have muscular adaptation, most likely a shift towards type 1 fibers through aerobic training. Went over that. Well, as during this, during aerobic training, you're going to have changes in heart size. Specifically, your left ventricle is going to go through hypertrophy. And we see here in aerobic exercise, usually we get thickening of the walls as well as increased diameter of the left ventricle itself. And then in resistance training, you get mostly thickening of the walls, and then the internal space here maintains its size. And so in aerobic training, not only are you increasing the amount of blood that can sit in the ventricle, but you are also increasing the musculature around it so it can eject more forcefully and push out more blood, hence a higher stroke volume. And then for resistance training, you're not really increasing the amount of volume in here, but you are increasing the muscle tissue around it so that contractility, that ability to forcefully push out blood increases. So you will see slight increases or slight gains in left ventricle stroke volume in resistance training, but you'll see even greater ones and more predominant ones in aerobic training. So looking at stroke volume in untrained versus highly trained individuals, you can see that there's a massive change. Going from an untrained individual to a very highly trained individual, you can get stroke volume to double in amount. You can go from 50 milliliters per beat to up to 110 milliliters per beat. And as well as we can see here, at any given treadmill speed at pre-training, we have our pre-training stroke volumes, and then at any given speed, your stroke volume is going to be higher, and which means higher cardiac output, as well as if your stroke volume is higher, that means your heart rate does not need to be as high, which means that the vasculature supplying the heart has more time in between each contraction to supply the heart with oxygen, which allows for you to work more efficiently. The heart rate adaptation, right? Resting heart rate is going to drop significantly. 1 beat per minute per week of training when you begin your training, as well as your submaximal heart rate is going to drop. So at any given intensity, your heart rate is going to be lower. And then your maximal heart rate is usually pretty much age and genetic dependent. And so you're not really changing your maximal heart rate. More of what you're changing when you get to maximal heart rate is your stroke volume. So we look at this as well as heart rate recovery with exercise aerobic training. You see after an exercise ceases, after you have finalized or stopped exercising, you see here individuals who have gone through training, post-training, will drop back to baseline much more quickly. This has to do with stroke volume, as well as this has to do with their ability to clear negative metabolites and allow them to return to baseline more quickly. Cardiac output is obviously with stroke volume and heart rate changing is going to increase. So we see here pre-training and post-training at any given intensity, your body has a higher cardiac output, which means more of a supply of oxygen to the muscles, allowing the muscles to produce more ATP. And so we see here the slight difference. Not only can you have a higher cardiac output at each given intensity, but also you can maintain higher cardiac outputs at even higher intensities than you were even previously able to work at. We'll see here on the left, here's another graph showing your stroke volume at any relative oxygen consumption. So if you're doing anything that requires you to consume 3 liters of oxygen per minute, if you are a highly trained endurance athlete, you're going to have much, much higher, as much as 40% higher cardiac output at any given training intensity. As well as we look here at any given training intensity, because your stroke volume is higher, your heart rate is higher. And again, this is really important for oxygenating the myocytes. If your heart rate is lower because your stroke volume is higher, that means the time in between each contraction is higher. So when the heart is beating, when the heart contracts, obviously blood cannot flow through it. But if we lower our heart rate at any given intensity, that means the time in between each contraction that allows the blood to reperfuse the myocyte and resupply the cardiac muscle cells with oxygen, that time increment becomes longer, which means greater oxygenation, which allows for your heart to function more efficiently. And that's why stroke volume is so important. That's why stroke volume adaptation is so prevalent in aerobic training, because you need to allow that heart time to relax and supply itself with blood. So we look at this, the oxygen needs of the muscle, right? The oxygen needs of the muscle, as exercise intensity increases, so does ATP demand. In order for you to continue that output and have that higher output during your exercise, it's because you have more ATP being produced. So in order to maintain higher exercise intensity, you need to have higher ability to produce ATP. So in response to this, the rate of oxidative ATP production increases. O2 intake in the lungs goes up, O2 delivery to the muscles and heart increases, and then oxygen storage is limited. Use it or you lose it. So what we're saying here is that the oxygen storage within the muscle is relatively limited. What we are actually really changing is the ability to transport oxygen to the working muscle and increasing that, which allows us to have higher ATP reductions. So training increases VO2 max. So as we would imagine, if VO2 max is the measure of aerobic endurance, aerobic capacity, as you train aerobically, you're going to see an increase in VO2 max. And so you see here at any given work rate, this is a VO2 max for an untrained individual, they stop and they peter out at about 10, 11 miles per hour, versus someone who's highly trained, not only do they have a higher VO2 max, but they also are able to go to higher speeds with their VO2 max. So not only are they consuming more oxygen at any given rate, but they are also, excuse me, not consuming oxygen at any given rate. Not only are they able to uptake oxygen at any given rate, but they are also able to move at higher paces for longer durations. We hear just some norms for relative VO2 max. We see here an average VO2 max for somebody of our age is about 44 to 51. I think I myself am right on the bottom echelon of this, probably closer more to the fair. I'm not a very aerobically fit person versus I know my sister's a very aerobically fit person. She likes to run half marathons, so I'm going to guess the last time, or I remember the last time that she did hers, she was somewhere around 48 to 52, which is very, very high for a woman. So her VO2 max per unit or per kilogram of body mass is higher than mine. So her relative VO2 max is higher. But since I'm a much larger individual, I would imagine that my absolute VO2 max is. Just because I'm larger, I need more oxygen, but her muscle cells are actually more efficient at utilizing that oxygen. With this, right, we still include anaerobic glycolysis, so moderate duration, breakdown of glucose into the, breakdown of glucose and glycogen from the bloodstream and from the muscles. This does not require oxygen, but this is important because this is what begins to produce lactate and acidosis. So we remember with aerobic respiration, with the oxidative system, it begins with glycolysis, and as we make the exercise bout more intense, that means glycolysis ramps up. And if we remember, when glycolysis ramps up, we start to have more negative outcomes. We start to have more negative metabolites accumulate and lead to not only glycogen depletion, but also the accumulation of our acidosis. So we see ventilatory responses, right? We see changes in our breathing. We see increased ventilation as we begin to exercise. And then we remember ventilatory threshold 1 and 2. So essentially, we're going to think about this as one concept, just to simplify it, though. If we remember my example before is why are you breathing right now? You think about it, why are you breathing right now? And why you're breathing right now is what we've talked about for all these lectures, is that your muscles need oxygen. So your respiration rate is driven by the oxygen need of the muscles. And what ventilatory threshold is the point at which your breathing increases exponentially faster than your actual oxygen need. Because if we remember the bicarbonate buffering system, the ventilation of CO2 out is what helps us buffer acidosis. And so, yes, you are ventilating more quickly than you need, so you are actually inhaling more oxygen than you can consume. But the point of that is for you to exhale out more CO2 to diminish that acidosis that is accumulating because you have gone past your lactate threshold 1 and lactate threshold 2. So look here, look at these individuals, a trained versus untrained individual, not only does, excuse me, sneeze, not only does the untrained individual hit this lactate threshold early, right? We see them hit their lactate threshold early. This means that they are going to begin to fatigue more quickly. But what we're noticing here is no matter how well trained you are, the accumulation of lactate is relatively the same slope. It accumulates at relatively the same rates. The thing that's occurring, though, is this individual, the trained individual, can get to about 78-ish% of their VO2 max before they actually reach their lactate threshold. So that means that they're likely running at a faster pace here when they reach the lactate threshold than this individual was. And this is really, really important for people who are trying to run a marathon. So you see over here the treadmill speed. So if you are a long distance runner and you can get to about 11.5 miles per hour and still be below your lactate threshold, you're obviously going to finish the rate faster than somebody who's running it at 8.3 miles per hour, because this person can only run at 8.3 miles per hour, because if they go over that, they're going to reach their lactate threshold, it's going to skyrocket, and they're going to fatigue. And so in this way, lactate threshold is kind of the speed limit or the upper echelon of your speed at which you can maintain before you become rapidly fatigued. So this lactate response is different interval length rest periods. So we see in an anaerobic interval training where you're doing 5 by 200s of 2-minute rest, even though you're having longer rest than if you're doing aerobic training, because the exercise is more anaerobic in nature, you're going to have greater lactate and acidosis accumulation because you're utilizing more glycolysis for this fast-paced exercise, which means more negative metabolic outcomes, specifically acidosis. As we go to a little bit more anaerobic glycolytic, you see here that their acidosis and lactate is accumulating not in as great a capacity as, let's say, a 200. And then aerobic endurance, aerobic oxidative system, because that energy system is so much slower and is not relying as heavily on glycolysis, but relying more heavily on the mitochondria and the oxidative system, you don't see as great of a buildup of lactic acid, or specifically acidosis. So while VO2 max is the best single measurement of aerobic fitness, it is the best determinant of aerobic fitness in normal populations or in general populations, it is not the best predictor of endurance performance for elite athletes, okay? So it's best for fitness, but not necessarily for endurance elite athletes. The best predictor of aerobic performance is often the ability to compete at a higher VO2 percentage of one's, a higher percentage of one's VO2 max. And we'll talk about that in a second here. So we see here for an elite runner, they're running the entire race at about 80 to 90% of their VO2 max. I would imagine, or I can guarantee you right now, if I brought almost every single one of you into the lab and had you run at 80% of your VO2 max, you would tire out very, very quickly. Most individuals would. Most individuals can't run for a longer period over anything above their 60% of their VO2 max. And so what we're seeing here is at any given running speed, 11.3, 12.9, runner B is actually utilizing less oxygen. They're doing the same amount of work, but they're utilizing less oxygen, which means at any given pace, they are at a lower percentage of their VO2 max. And so you can imagine if you extrapolate that over time, if at 12.9 miles per hour, right, runner B is only at 32% of their VO2 max, and let's say like at 16.1 miles per hour, they're only at 55% of their VO2 max compared to athlete A, who is at 63% of their VO2 max. Athlete A is going to reach 100% much more quickly than athlete B, which in essence is saying that athlete B is more economical. And so if these two have relatively the same VO2 max, the more economic individual is going to have greater endurance and greater capacity to perform the race at a quicker speed. So running economy has to do with body composition, your running style and gait. So what your weight is, how that distribution of weight manifests versus your legs and your legs versus your arms, your running style and your gait. So something I like to say is a lot of explosive athletes run in a very bouncy manner. When they run, they bounce a lot because that's what's indicative for their sport. It's they need. You have a lot of explosive movements up and down, and so you need to run in a certain manner that allows you to explode. Versus marathon runners are very, very efficient in their manner. Their vertical motion is only there so that they can pick their foot up and move it to the next foot strike or foot placement. So they don't have a lot of wasted motion. So if you watch a marathon runner's hips versus, let's say, like a sprinter's hips, a marathon runner's hips barely move up and down, versus a sprinter's hips will move up and down more because they need that vertical ground reaction force in order to explode into their next stride. So the kinematics and kinetics, so force and motion, shoes, ground contact time, biometric stiffness, aerodynamics, all these things play into your running economy. And so if you're larger, obviously you're going to have lower aerodynamics. If you have worse shoes, it's not as good for you. If your biomechanics and how you move through your movement aren't efficient, it's going to be less efficient. Looking at things like mobility, function, range of motion. So if you are a little bit more functional in your range of motion, if you are able to produce force a little bit better at certain ranges and certain foot strikes, it might be more beneficial for you during your aerobic race. So here's just an extreme example of bad form versus good form. Obviously, as a child, you generally don't have very good running form versus somebody who's aerobically trained. You can see his hips here are very, very quiet, barely moving up and down to make him more efficient as he tries to move forward. Looking at this again, we can see in a recreationally trained individual versus a highly trained or elite individual, an elite individual is only using about 40 milliliters per kilogram per minute at the same speed as a recreational athlete using 47.4. So not only does the elite endurance athlete have a higher VO2 max in general, They have a higher VO2 max than the recreationally trained person does in general. But at any given pace, they are utilizing less oxygen to do the same thing. You might be thinking, well, if they're utilizing less oxygen, they might be running slower. No, what this is saying is at the same exact given speed, kilometers per hour, the elite athletes are using less oxygen, which means they are utilizing less energy to do the same amount of work, which means that they are more economical. So you're also going to see muscular adaptations. So you're going to see greater AVO2 difference. So the ability, the myoglobin within the muscle, the ability of the muscles to extract and utilize that oxygen is going to increase. You're going to see a type 1 fiber shift and hypertrophy of those type 1 fibers, mostly due to sarcoplasmic hypertrophy and increase in mitochondrial density and size. You're going to see myoglobin increases. If we know what hemoglobin is, remember hemoglobin is the oxygen transferring group of the red blood cell that brings oxygen to the muscles. Myoglobin is the same thing, but within the muscles. Myo meaning muscle. So myoglobin is what transfers oxygen within the muscle, as well as capillary density increases. So you can go through what's called angiogenesis, where you begin to increase the amount of capillaries, the spider web of blood supply to the muscles. And if you're surrounding the muscles with more blood supply, that means more diffusion of oxygen. As well as you'll see increased mitochondrial size and number, like I said, and then increase oxidative enzymes. So all the enzymes we see in glycolysis, so we'll go back. Maybe I should have gone back. That's a dumb decision by me, but we're going to keep going. We see all the enzymes. Shouldn't have gone back at all. We see all the enzymes that are involved in, probably my first slide, isn't it? Yeah, it is. Good job, Trevor. So all the enzymes that are involved in the Krebs cycle, and they're not even here. They're not even listed. It's a good decision by me. All the enzymes that are involved in the Krebs cycle and the electron transport chain, though, there's so many of them that if we increase the amount of oxidative enzymes, we're going to have a massive increase on the ability of the oxidative system to produce ATP for us. And now the long scroll back to where we were. Almost there. There we go. And here we see with aerobic training, you get a massive shift towards type 1 fibers. In strength and hypertrophy training, specifically more hypertrophy training, you get more of a shift towards type 2A fibers here. And then in speed and power training, you get this shift towards the fast twitch type 2X fibers. Your blood volume is also going to change with training. So not only are you increasing total blood volume, but you are increasing the red blood cell counts, or red blood cell volume, and the plasma volume. And the reason that you don't just increase red blood cell volume is if you were to do that, your blood would become more viscous or more thick, and it would be more difficult for your heart to pump that blood around your body. So you're actually increasing both amounts of your in the blood, both the blood plasma and the red blood cells. Even though hematocrit percentage is going down, the absolute amount of hematocrit is going up, which allows for more oxygen transfer. So ventilatory adaptation and aerobic training, no significant changes in lung structure or function. So your lungs are not what is really changing. In an elite trained individual versus a novice trained individual, you're going to see very little difference in their lungs. Now, if you have someone who's diseased, you might see a difference in their alveoli. But for the most part, general population to elite population, there's relatively no difference in lung size or lung function specifically. However, your ventilation will change. The amount of times that you can ventilate per minute in a trained individual will increase almost twofold. You will increase almost 100 liters per minute of inspiratory capacity when you are a trained individual versus a non-trained individual. Well, as diffusion increases due to increased lung perfusion. So you're not really changing the amount of alveoli in the lung, but because you are changing the amount of blood being pumped to the lungs, and because you are changing the amount of air that's moving in and out of the lungs, that is what allows for more oxygen diffusion, actually not any increase in the alveoli themselves. Again, looking at the rate of glycogen depletion, we talked about this before, as exercise time increases, you're going to have higher glycogen depletion. Consuming carbohydrates during prolonged exercise increases performance. So as you begin to go through long duration exercises, you're going to start depleting muscle glycogen. You want to keep your intake of glucose relatively high so that you can continue your exercise here. So you want to have 30 to 90 grams of carbohydrates per hour for events over an hour. So if you're playing a football game, if you're running a marathon, whatever it might be, you want to be consuming sugary beverages so that you can be maintaining that blood glucose. And I can imagine some of you are sitting there going, no, it'll dehydrate you, the old misnomers of what carbohydrate drinks do to you. If you want to argue with it, you can read a lot of literature on it, as well as you can look at every single elite endurance athlete, triathletes, marathon runners. You will see that they are being given carbohydrate gels, extremely concentrated carbohydrate gels for them to eat while they are running or drink while they are running, so that they can readily replenish the depleted glycogen stores within their muscles. And so for those of you who are in the class who are long distance runners, some of you may be also long distance runners. If you were doing long distance running, don't be drinking just water. Make sure that you were drinking sugar or carbohydrate beverages. And that, if you don't believe me, there's a lot of literature out there that supports this. That's where this information is coming from. You want to use simple sugars. So you want to use glucose and fructose because those are very, very simple to use. So fruits, fruity beverages, those are usually the best used. But you want to make sure ingesting carbohydrates, solutions with high concentration cause GI issues. So you want to make sure that you're getting used to it. Most GI issues can be solved by long-term exposure. So if you have a high carbohydrate beverage, if you drink that a few more times, you will get used to it. I remember when I was young, I would go to my aunt's place, and being the aunt that she was, she'd buy us pretty much whatever we wanted. And when I was at home, I never got to have Powerade. So I remember the first year I went there, I drank a ton of Powerade and I got extremely upset stomach from it. It actually was so bad, I had an upset stomach for probably 2 or 3 days. But that was because I had this massive influx of carbohydrates that I had never had before. Now, into my adulthood, when I play sports, usually if there was a hot game while I was pitching, I'd be on the mound for 7, 8, 9 innings, and I'd throw 100 or so pitches. I would probably go through a couple bottles of water and a couple bottles of Gatorade in that day and never had stomach issues because I just was more used to being able to consume those carbohydrates. As well as we look at carbohydrate loading can increase glycogen stores. So if you increase or if you carbohydrate load correctly, you are increasing your baseline level of glycogen, which allows for you to utilize more glycogen over time. And what this graph on the left is showing us is that even in a group where we deplete glycogen, this 0 hour point, we deplete glycogen initially with some sort of extreme exercise bouts. If we supplement with carbohydrates immediately right after, we can see a baseline, or we can see our glycogen go back to normal and maintain near normal levels, even though we had this massive 60 millimoles per liter drop in muscle glycogen. Now, if we were to add another graph to this and we were to say, okay, put them through glycogen depletion, but then give them no replenishment, they would maintain and they would stay much, much lower. And obviously, as you can imagine, if you have less muscle glycogen, you can't produce ATP as fast, and therefore you can't perform at as high of a clip. And so there's two different types of carbohydrate loading strategies. So there's the classical one where you have 4 or 3 days of low carbohydrate loading, and then you have 3 days of extreme carbohydrate loading and your training being tapered, versus contemporary, where you have just normal training with no carbohydrate load, and then you get into extreme carbohydrate loading. To put this in reference, if you were to do 10 grams per kilogram, for me, that would be somewhere near 900 to 1,000 grams of carbohydrates in the last day. And so what this contemporary one does, this is becoming a little bit more popular as we found, is when you have no carbohydrates for these training days, your body essentially becomes a little bit starved for carbohydrates in a manner. And what it does is it begins to upregulate the receptors that transfer glucose and sugar into the body. And so when you have this massive dump of carbohydrates at the last couple of days, now you are getting relatively the same total amounts of carbohydrates as you had if you were doing the classical way. But because you've kind of starved yourself and you have made the body more readily able and more willing to take in carbohydrates, you get potentially a higher total amount of carbohydrates being stored in the muscles. And so this is kind of the opposite of what you would do with protein. Remember, we said with protein, you would have the 20 to 30 gram feedings instead of the 40 to 50 bolus feedings. For carbohydrates, you can kind of do it either way. Now, there's a lot of evidence that is showing that this may be more beneficial in elite athletes, while this may be more beneficial in novice or moderately trained athletes. However, for most people, the classical method is recommended just because it is more feasible. If you've tried to have 1,000 to 12,000, or excuse me, 1,000 to 1,200 grams of carbohydrates in a day, it's pretty difficult. You'd have to be eating a lot of very hard or a very high carbohydrate meals, as well as like we said with the story about my Powerade consumption when I was young, is that if you were not used to this, if you decided, okay, maybe I have some athletes in here, maybe I have um, volleyball player in here, okay? And let's say they want to carbohydrate load for the next event. I would not recommend doing the contemporary loading because you are not going to be used to this massive dumping of carbohydrates right here. More than likely, you will get nauseous from it. You would need to slowly train yourself to do the contemporary carbohydrate loading. And once you've trained yourself to do it, once you've eased yourself into that, then it may be more beneficial for you. So in summary here, the contemporary one may be more beneficial overall, but it is much harder to get used to it and takes a lot more prep than the classical model and doesn't supply like a massive difference. It is a little bit of a difference. So if you're like an elite athlete and you want that 1 to 2% edge, it's good for you. But for most athletes, it's not going to be that useful. So look at this, our summary here. Tidal volume and respiratory or respiration rate increase with exercise. So the amount of air that we can breathe in and the respirations themselves increase. Heart rate increases linearly with intensity. So we know that as you begin to work out harder, your heart rate is going to increase. But if you are increasing stroke volume, your heart rate does not need to increase at as high a capacity. Blood flow is being redirected throughout the body. More blood is being moved to the muscles. So as you exercise and as you become trained, you are better able to shunt blood to the muscles and better able to utilize the oxygen in that blood. Make sure we know what cardiac drift is. Make sure you know what's occurring and what the mechanism is behind it. Aerobic, and which is mostly saying it's happening because of dehydration. So as dehydration begins to limit the amount of blood flow in your body, what's happening and what are the compensatory reactions that are happening? Aerobic performance is based on a variety of factors: VO2 max, lactate threshold, economy, and local muscular adaptation. Know what's occurring there. Left ventricle hypertrophy is causing increased stroke volume. So remember, with our aerobic athletes, we're getting not only increase in the diameter of the left ventricle, but also increase in the musculature, which allows for more stroke volume. And in our resistance trained athletes, we see an increase in the musculature, but not really an increase in the diameter. It stays about the same, but that also still allows for greater contractility and more stroke volume, hence more blood flowing out per heartbeat. And the higher lactate threshold allows for aerobic performance at a higher percentage of VO2 max. Remember, if your lactate threshold is higher, that means you can maintain a higher pace throughout the race without going over your lactate threshold. And if you're maintaining a higher pace, that means you're running faster and your times are going to be quicker. But that pretty much sums up the end of this lecture. For those of you who are still really interested in learning more about this, you can reach out to me. I'll be happy to ask you questions. If not, I hope you guys have a good day and I'll see you next time.